Hey there, Miss Heaton signing in to talk about advanced roadmap stoichiometry. Hopefully by now you are a little bit of a pro in doing grams to grams calculations. Today we're going to throw in some weird stuff to enable you to do more stoichiometry, more different kinds of conversions. So it'll make you more versatile at calculating using chemistry. We're going to talk about three different kinds of conversions that we haven't done yet. The first is converting from moles to atoms. And the conversion factor here is that 1 mole, you hopefully already know this, 1 mole is 6.02 times 10 to the 23rd particles, meaning molecules or atoms. Excuse me. So to try this out, we're going to consider this equation. We're going to use this one all day today. This is our one equation we're going to use. And the question I have for you using atoms is this. How many molecules of O2 are needed to react with 123 grams of iron? I like to box in the thing that I'm looking for and underline the thing that I'm starting with. Then you could look at this handout that you hopefully got from your teacher and kind of look at what you know. You know the mass of something. Ignore that word limiting reagent for now. So this is where we're starting, and we want to figure out how many molecules, which is a kind of particle, of something else we have. So you can see here that there's going to be 3 steps. We're going to convert from grams of Fe to moles of Fe, and then from moles of Fe to moles of oxygen using our mole ratio. And then finally, using our new piece, this moles to particles ratio, we'll convert from moles of oxygen to molecules of oxygen. So let's dive in and do that. So we're starting with 123 grams of iron. And the first thing we want to do is convert that to moles. Using our periodic table, we know that 1 mole of iron weighs 55.9 grams. We put grams on bottom so that they will cancel out. That was our first step. Step 2 is to convert from moles of iron to moles of oxygen. And from our balanced equation, we see that there are 4 irons for every 3 oxygens. Since we have moles of irons in our previous step, we want to put moles of iron on bottom, and that mole ratio is 4. And we want to put 3 moles of oxygen on top, so that the moles of iron and moles of iron will cancel, and we will have units of moles of oxygen. And then last but not least, we want to convert those moles of oxygen into molecules of oxygen. And we know that 1 mole of oxygen is 6.02 times 10 to the 23rd molecules. We'll put 1 mole of oxygen on bottom, and 6.02 times 10 to the 23rd molecules. And there's no good abbreviation for that. Maybe use MOLEC of O2. So moles of O2 and moles of O2 cancel. And now we're ready to type this into our calculator. And I've got my handy dandy little TI faker here. So you'll type in 123 times 1 times, whoops, that's not working. 123, I guess I have to hit the button here, times 1 times 3 times 6.02. We'll use the E button so we don't have to use parentheses, E23, divided by 55.9 divided by 4. And I got 9.93 times 10 to the 23rd. Everybody always leaves this part off at the end, but you should know that if you're calculating molecules, it's going to be a pretty darn big number. So that's the number we will write as our answer. So our answer is 9.93 times 10 to the 20, was it 23? Oh yeah, 23 molecules of O2. Now looking at sig figs, we look at the number we're given, 123. It's got 3 sig figs, so our answer should have 3. And it does, because remember in scientific notation, anything before that times sign counts as significant. Oh, hey, look, I even wrote the answer in there, so to make sure I got it right. Good deal. Let's try another one. Okay? Now, a lot of times we want to look at a gas, and an easy way to measure a gas is in liters. And there's actually an even easier thing here, that if you are at STP, remember STP is 1 atm of pressure, standard pressure, and the standard temperature of 0 degrees Celsius or 273 Kelvin. So if those are your conditions, you can use this super easy conversion that 1 mole of any gas is going to take up 22.4 liters. That's like 11 bottles, 11 2-liter bottles of soda. So let's do this calculation here. How many moles of Fe2O3, that's what we're trying to find, would be produced if 11.5 liters of oxygen react with excess iron at STP? Okay, key thing here, we're at STP. So if we know liters at STP, that's 11.5, and we are trying to find moles of other thing. Oh look, this is going to be pretty easy. We're just going to go from liters of O2 to moles of O2 to moles of Fe2O3. So it's only 2 steps. This will be really easy. So we'll start with our 11.5 liters of oxygen that we were given. And to go from liters to moles, we know that 1 mole is 22.4 liters. Oops, let's see that. There we go. 1 mole is 22.4 liters. Since we want liters to cancel, we'll put that on bottom. And we'll put moles of O2 on top. So 1 mole is 22.4 liters. So then liters of O2 will cancel with liters of O2. And our units are now moles of O2. And we want to go to moles of Fe2O3. So we'll put moles of O2 on bottom and moles of Fe2O3 on top. If we look at our ratio here, it looks like there's 3 oxygens for every 2 iron 3 oxides. What did I just say? I forgot already. 3 to 2. 3 O2s for every 2 Fe2O3s. So then moles of O2 and moles of O2 cancel out. So 11.5 times 2. Well, let's type this into our calculator here. 11.5 times 2 divided by 22.4 divided by 3. And that turns out to be 0.342. 0.342. And let's make sure that's the right sig figs. We had 3 here, so we need 3 in our final answer. Oh, 0.342, that has 3. And our units are going to be moles of Fe2O3. That is our answer. Let's see if that's reasonable. We've got 11.5 liters. That's about half of a mole. So to end up with about a third of a mole, that seems reasonable. Oh, but hey look, and there's my answer right there. So nice of me to put those in there for myself. Okay, now where it gets a little bit tricky is if you are not at standard temperature and pressure. At those conditions, you have to bust out that handy-dandy ideal gas law. Yeah, I know you're excited about it. Just to remind you, in the ideal gas law, pressure has to be in ATMs, V has to be in units of liters, N stands for moles, which we now know a lot better than we did back in Unit 3. R is 0.08206, and T has to be in Kelvin. This is a great review for the final exam. Aren't you excited about that? Okay, so here's how a problem that uses the ideal gas law would look. How many moles of Fe2O3, that's what we're trying to find, would be produced when reacted with this much oxygen at this pressure and this temperature? So it looks like we've got a V, we've got a P, and we've got a T. Whew, okay, so we're trying to find moles of Fe2O3. That's moles of our unknown. And we are starting with liters not at STP. So first we're going to use Pivnert to go from liters of oxygen to moles of oxygen. Then we will go from moles of oxygen to moles of iron 3 oxide. So it's just like the previous one, except instead of using our handy-dandy 22.4, we have to use Pivnert. So this first step, to go from liters to moles, will be to plug in the numbers you have for PV equals NRT. We're going to be solving for moles. That's our unknown. So let's plug in what we know. We know that the pressure is 2.66 ATMs. That's the right units. V is 11.5 liters. That's the right units. N is what we're trying to find. R is 0.08206. And T is 298 Kelvin. Okay, we will bust out our handy-dandy calculator here. Let's rearrange this. So we'll have 2.66 times 11.5 on top, And on bottom we'll have 0.08206. Let's put this all in the parentheses so we remember to type that in right. Times 298. Okay, so we'll type in 2.66 times 11.5 divided by 0.08206 divided by 298. I got that N, the number of moles, was 1.25 moles of oxygen. Okay, so, oops, my picture kind of shifted here. But now we've got moles of oxygen, and we're trying to find moles of Fe2O3. So we look back at our balanced equation. We see that there's 3 oxygens for every 2 Fe2O3s. So we'll take our 1.25 moles of oxygen. I'm just going to tag this right on here. We're going to use the mole ratio. We want moles of oxygen on bottom so that it cancels out. We'll put moles of Fe2O3 on top. And I already forgot again. You'd think I remember, like the third time through this. Here we go. 2 to 3 ratio. So we'll do 1.25 times 2 divided by 3. And I got 0.833 moles of iron 3 oxide. And sig fig wise, if we look at what we're given, it's got 3, 3, and 3. Excellent. So we got 3 in our final answer. Oh, and look, there is the answer. So we can check our work, we did it right. Okay, here folks, here's one to try on your own. So try this, hit the pause button, and when you got it, unpause, check your answer. Here's the answer. You should get 67 liters of O2. If you got questions about it, try to look back and see what specifically you got and bring those questions to your teacher tomorrow. Happy road mapping!